Hi students. So we were talking about this single chains in polymers, and here I will elaborate on the calculation for end-to-end length in a further detail so that you can get the derivations correct. So what we have till now is this freely jointed polymer chain model where you have n number of such monomers who are capable of orienting in any random direction, right? So any random directions are allowed, and you are considering that each of them can be denoted by these small vectors r1, r2, etc. So here I have assumed a chain which has 10 polymers. It can grow further. Let us consider here 10 is our maximum length, capital N, right? So capital N is the number of polymers in the chain. Now from our previous discussion, you already know that we were trying to define some length, some characteristics length called end-to-end length. End-to-end length, which is basically telling you that where the end, the last point of the initial monomer is first monomer is, and where the head of the last last monomer is, that is the nth monomer is. So you join these 2 points with this line, and this estimates that how coiled or how open up this particular polymer chain is, how spread out or how coiled this particular chain is. So this particular vector RE is your end-to-end length, right? So to measure that what this RE will be in terms of the features of the monomer chain, that a polymer chain, that is the length of each of the monomers, what we considered is we considered another origin 0 0. Let us consider this to be the origin, and with respect to this particular origin, we define some position vectors for each of these monomers initial and final point. So what we do is we join these 2 points. Let us call this particular vector that we have here, this vector is r0, and that is the position vector of the first point, the tail of the first monomer. Then we join this point, and this can be called r1, that is the head of the first monomer, where the head of the first monomer is at that point exactly the tail of the second monomer is also there. So this is that position. Like that we can create all these position vectors r2 and so on. So the last one in this lot here will be rn, right? Rn will denote that what is the last point of this polymer chain, the head of the last monomer. Now let us try to figure out this end-to-end length Re, this quantity, with respect to these vectors, so that we can reflect back upon the properties of the monomer itself, right? Each monomer itself. So if I want to figure out what is Re, let us use the vector algebra. So Re, from the triangle law of vector addition, you know that suppose this is one vector, vector A, this is another vector, vector B. The triangle law of vector addition tells me that this vector, vector C, is going to be the addition of the first 2 vectors. So the thumb rule is that you maintain the directions. If this is pointing in this one, the second one should also point in the same way. The arrow should be in coherence. The addition vector will have an arrow which is not in coherence with them. That is, if you have this one in this direction, this one in this direction, here the direction of C is not going to be like this. No, this is wrong, right? So the direction of C has to be like this only. So this is how the directions are decided, and this is how you perform the vector addition. So let us use the vector addition to figure out what RE is going to be. So we focus on this particular triangle. This, and this, right? So this is R0, the point is towards this, right? This is RE and the point is towards this, right? And this is Rn and the point is towards this. So this clearly reflects this condition, right? So what is Re then? So in general I can write from the triangle that we have is that Re is going to be Rn minus R naught, right? Because from here, following the same rule, we can write that R0 plus Re is equal to Rn, right? So in this notation, R0 is this direction, Re is also this direction. So A and B, and C is going to be the other direction. So C is going to be the other direction, and that is your Rn. Rn is in the other direction, right? So this is what comes from the vectors law of addition of the triangle law, and from there we write Re is equal to Rn minus R0. Okay, good. So if we understand this, now let us leave R0 apart and let us focus on Rn. What is Rn? Rn is this vector, right? This is your Rn. Focus on this Rn. So Rn can be also written in terms of Rn minus 1. So this is Rn minus 1. This is Rn minus 1. So remember that we were drawing all these position vectors, right? R0, R1, R2, R3 is going to be R4, R5, R6, R7, R8, R9. So Rn minus 1. Here our n was 10, so R9 is this one, right? So Rn minus 1. Now if you focus on, instead of that previous triangle, now if you focus on this triangle, this one, and this one. If you focus on this triangle, then what you have? This is Rn minus 1. This is R0 and they are pointing, they are in coherence. So their addition is Rn, right? So this R10, or which is in general I can write Rn, right? In terms of that you can write what your R capital N is. So let me write that. Capital Rn from this triangle could be written as capital Rn is equal to capital R n minus 1, right? Capital R n minus 1 plus this, that means R10, 10 is n here, so Rn. Okay, let us take this and replace here. So what do we write? Instead of Rn we write Rn minus 1 plus small r capital N minus R0. Fine, great. So Rn minus 1 is again could be written in terms of Rn minus 2 in the same way, right? So we go on doing this again and again. Now this time you will replace Rn minus 1 instead, leaving the other two terms intact, and Rn minus 2 will be used instead. So what we will write, just from analogy you can say that Rn minus 2 is going to be, here we will write Rn minus 2, Rn minus 1, that is going to be your Rn minus 1, capital Rn minus 2, small rn minus 1 plus small r n minus R0, right? So this way you can go on doing this, replacing the first term at each and every step. So you started with Rn, then you will get n minus 1, then you will get n minus 2, n minus 3. Like that you will go on doing this, and each and every time you will get one small r terms extra coming into this as a summation. So R0 will remain. First you will get R capital N, then you will get small r capital N minus 1, small r capital N minus 2, N minus 3, N minus 4, and so on. They will keep on coming, right? So in this way if you do the entire derivation, if you go on doing this again and again, so what will result? You will get rid of all capital R's. All capital R's will be gone, because at the last step, when you will be in the last triangle, what is the last triangle? This is your last triangle. This is your last triangle. This one, and this one. So mind again the direction of the arrows. In the last triangle, you will have capital R0, right? Small r1, that will replace your r1 from the previous step, right? Capital R1 will be replaced by r0 plus r1. So in the last step, what you will have? You will have capital R0 plus small r1, and then by that time you have r2, r3, r4, everyone present here, r2 plus dot dot dot, and then finally these two terms n minus 1 rn, and finally r0. This r0 remains here, right? And they two cancel each other. As they cancel each other, you are left with ri summation, r1 plus r2 plus r3 plus dot 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 rn. So we write n is equal to 1 to capital N ri summation. These ri's are basically your monomer vectors, each and every bond vector. And now we gradually moved from a reference frame where we were considering an origin. From there we gradually moved directly on top of the polymer itself, right? So we are now on top of the polymer itself. So we are traversing along the polymer like this, right, through the bond vectors and summing it up. So this is how you get the expression for Re. So let me just now continue this discussion and discuss that how you get the final expression, right? What will be the steps after this to get the final expression for Re mod square. So we saw that instead of going with Re, we defined this quantity Re square and averaged it. And we are measuring this quantity, and our final expression was this was equal to NB0 square, right? So let us try to prove this from whatever we have so far. So far we have that Re is given by summation over Ri, n is equal to 1 to capital N. That is what we have, right? So now we have to find Re square and then average it out, right? Re square and then average it out. How to find Re square? Re is a vector, right? So Re is a vector. So if I want to find Re square, what do we do? Re dot Re. That gives me Re square. So let us talk about dot products a little bit here. So what is dot product? Suppose you have a vector A, which is given by, say, a1 I hat plus a2 j hat plus a3 k hat, right? So this is the vector. So if I want to find out that what is a square, then what do I do? A dot a. If I do a dot a, then what will happen? a1 I hat plus a2 j hat plus a3 k hat, a three-dimensional vector, dotted with again a1 I hat plus a2 j hat plus a3 k hat, right? Dot product means if you take a dot product of I with I, then it is 1. If you take dot product of j with j, that is 1. And if you take cross terms like I dot j or I dot k, they are 0. So the only term surviving will be a1 square plus a2 square plus a3 square. Something like that will happen, right? Let us do the same exercise for Re's to figure out what my Re square is going to be, right? In general. So in general, my Ri's are not written in terms of this I hat, j hats, but they are written in terms of summation of these Ri's, small Ri's, right? So my Re square is going to be Re dot Re, which I can write like this. Sum over Ri, that is my Re, n is equal to 1 to n, and sum over Ri again, right? So what should be my index? Let us take another index, otherwise I will confuse. So m is equal to 1 to n. They look same, right? If you break this up, this is also r1 plus r2 plus r3 plus r4 dot 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 rn. Same here, r1 plus r2 plus r3 plus r4 dot 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 rn. Why I have taken m here and n here? Because let me, if I open this up, these two brackets, in the first bracket I have r1 plus r2 plus r3 plus dot 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 rn, and dotted with r1 plus r2 plus r3 plus dot 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 rn, right? So if I take a dot product of them, what do we have? There are two kinds of terms that we have. First set of terms are like r1 square, then this multiplies with this, r2 square, r3 square, and so on, right? So r1 square plus r2 square plus r3 square, and so on. So these terms are one set of terms. Another set of terms are like this, r1 r2 dot product, r1 dotted with r2, r1 dotted with r3, and so on. So there will be also terms like r2 dotted with r1 and r3 dotted with r1. They are also going to be there. So why I am talking about these terms? Because r1 dot r2 and r2 dot r1 are same. Same for here. r1 dot r3 and r3 dot r1 are same, right? So you will have several such terms. So these two summations is what I have written in that slide as this. That this first summation can be written as summation over n is equal to 1 to capital N Rn square. That is the squared terms. And those which are not squared, they can be written as summation over R n, Rm, two indices, right? These two indices are different. Here the indices are different. Here the indices were same, that's why they got squared up easily. Here the indices are different, so I need two indices. N not equal to m, right? N not equal to m, but both of them can run from 1 to capital N. Both of them can run from 1 to capital N, and I have double terms. One I have like R1, R2, and I also have R2, R1. So 2. 2 times Rn, Rn vectors dotted. Okay, so this is my Re square. Now I take the average. So I take the average here. I take the average here. These terms all should be averaged like this, right? And I take the average here also. Okay, so when I take the average in all these three parts, what I see is that when n is not equal to m, that means you are multiplying two statistically independent vectors. You are taking a dot product of them. That means what you are actually doing is Rn dot Rn, and these two terms are both statistically independent of each other, right? So that means you are taking dot product of any two random vectors, and that is going to be 0 when you average it out, right? If you take any two random vectors and you take a dot product of them, then on average both of them can be in any direction and the dot product is going to be 0. So that is why this term results to be 0, the cross term results to be 0, just as it happened here. Like only the square terms survived. Here also only the square terms will survive. And what is Rn? Rn is basically bond length. Each of these bond lengths, if you consider them to be equal, then this is nothing but B0, right? This is B0, what we assume to be B0 in the first place. Each bond has a length of B0. All of them are B0 long, right? So that means you are summing up B0 square how many times? N times. You are summing up B0 square N times, right? So we sum it up, that gives me N times B0 square, and that is how you arrive at the solution. Okay, I hope you would be able to do this. Try it out once and let me know if you still have some doubts.